3D printing and magnets, a great combination or polar opposites? Find out in this episode of The Cool Parts Show. This episode of The Cool Parts Show is brought to you by Carpenter Additive. The company's Powder Life solution is a combination of hardware and software technologies designed to help AM users manage their metal powders. Stay tuned after the episode for more on how the system works.
I'm Pete.
I'm Stephanie.
Welcome to The Cool Parts Show.
This is our show all about cool, unique, interesting, amazing 3D printed parts. And what better place to find them than the manufacturing demonstration facility here at Oak Ridge National Labs.
We are working with Oak Ridge on a variety of episodes of the show on various additive manufacturing successes. And this one, Stephanie, I feel like is really attractive.
You could say that quite literally, because today's part is a 3D printed magnet.
Okay, so before we got into this, I didn't even know you could 3D print magnets. We have learned a lot. Stephanie, what are some of the issues with magnets?
Good question. So conventionally, magnets are made in a couple of ways. One is through molding, where you are molding the magnetic material and then sintering it to its final density. That puts a lot of restrictions on the geometries that you can achieve, and if you need to change the size or shape of the magnet, you need new tooling. The other way might be to start with a big block of magnetic material and to slice and dice it down into the sizes and shapes that you want. That can lead to a lot of waste. You might be losing as much as 50% of the material off of that original block.
And that's a big deal, isn't it? Reducing waste is a big deal because this is a difficult to obtain material.
That's right. Magnets are made from rare earth elements. Specifically, what we're talking about today is neodymium iron boron, which most of that is mined in China today. There's actually no domestic source here in the US. So this is a materials issue, but it's also a supply chain issue. Part of that is because magnets are in so many of the things that we use every day. They're in motors and generators and things like that. That's why Oak Ridge, as part of the Department of Energy, is so interested in this problem, and they're studying it through their Critical Materials Institute. Let me introduce Parans Paranthaman, one of the corporate fellows working on this project, to describe why this research is so important.
So magnets are used like sensors, motors, generators, or the magnets are used in speakers, or if you want to store a data in a computer, or magnetic resonance imaging. And also if you take your car, the one we drive every day, it has like 37 kinds of magnetic parts there. Typically, these are rare earth metals or rare earth oxides, what we call is lanthanides. So this Critical Materials Institute, it was created in like 8 years ago, and it's a US Department of Energy's Energy Innovation Hub, hosted by Ames Laboratory and Oak Ridge National Lab, Idaho National Lab, Lawrence Livermore are part of it. The key thing is we want to focus on materials that can be used very efficiently in any of these magnet applications or clean energy. And we want to have American competitiveness for clean energy. And the challenge is we want to have domestic supply chain for any of these. Either you want to use the material efficiently, or you want to replace the critical materials, or you want to recycle.
Okay, so reducing waste. We've done other episodes of the show that sort of explored that. The way that 3D printing lets you control, minimize, even optimize how much, how little material you use. And that's really important here. That's a very big deal here because of the material involved. Let's go to the beginning. How do you do that? How do you 3D print a magnet?
So they've tried a couple of different methods. You can do it through laser powder bed fusion. You can do it through binder jetting, which is sort of similar to that mold and sinter process. But the technology that's maybe furthest along is the one that's right behind us, the BAAM, the Big Area Additive Manufacturing machine.
Okay, so yeah, BAAM, Big Area Additive Manufacturing, a platform from Cincinnati Incorporated, an extrusion 3D printing process, building parts layer by extruding material. Significantly, it doesn't use like coils of material that are custom made for 3D printing, but instead it uses pellet material like you might use in injection molding, say, which sort of gets to my question, like BAAM is for polymer and magnets are metal, right?
So that's a good question. So what they're printing here is actually a polymer bonded magnet. So that magnetic material is mixed in with thermoplastic. That's what the printer is extruding, and so it prints like a plastic, but it functions like a magnet.
This seems like a dumb question, but it's It's magnetic, right? How do you print with it? Like, doesn't it stick to the metal in the 3D printer?
Not a dumb question, something that I did not understand at the beginning of this. So actually, as you are building up the geometry, the magnetic material is not magnetized. You build the whole form first, and then you magnetize it all at once. I'll let Parans explain how that works.
A lot of times magnets, it has a Curie temperature. So if you take the neodymium iron boron, the Curie temperature is slightly above 300 degrees Celsius. So once you take this magnet, anneal slightly above 300 degrees Celsius, it becomes non-magnetic. Once you take the printed magnets, if you expose to a magnetic field, immediately it magnetizes.
Okay, so they're experimenting with creating magnets through 3D printing. They're using the polymer as a carrier for the magnetic material. I guess I've got a lot of questions about that. Like, is it really that easy? Are there challenges to 3D printing magnets? Is there further that they need to take this idea?
Yeah, so challenges. We talked about how the material is this composite. It's a combination of the magnetic metal and the thermoplastic. And that in itself is a challenge. You want to maximize the amount of magnetic material in the magnet because that's what provides the strength. But at the same time, you can't go too far or else you'll lose the properties of the plastic that make it printable. So that is a challenge.
BAAM or FDM process, the challenges is first the magnetic properties. How close to the full density magnet. There are methods where you can use sacrificial binder. You can mix it with that and do post-processing where you can do the sintering and there will be a small contraction in size, but one can get full density. But these are challenges. Can we do it with this magnet composition to achieve full density? Because higher the loading and the performance goes exponentially. And the magnetic performance, especially like energy product, it's like directly proportional to the square of the volume of material, magnet material present in a composite. So let's say 70 volume percent, 0.7 square, you get only 50% of your starting magnet powder. So if you want to achieve full density, you want to increase the loading. That's one challenge. And the other challenge is we want to have like mechanical properties. So you are mixing polymer and thing. So we have to maintain the mechanical properties. So that's another challenge. And surface finish, like defects, porosity, we talk about various challenges we have associated with printing. That's one thing. And another key parameter is there are anisotropic and isotropic. Anisotropic magnets, where you would align the magnets, everything into the perpendicular direction in one direction so that the magnets can be very strong. Even if you take a small printed magnet, it can be strong enough to use in a small, like cell phone speakers. So we want to align the magnets while printing. So we are doing research right now and like fixing this pulse magnetic field or field around the nozzle and print and align all at the same time. So these are the challenges we are looking into.
So there's this theme that keeps coming up on the Cool Parts show, and it comes up so frequently, it's like, it feels like habit to us now. And it's, you choose 3D printing, you choose additive manufacturing because it solves a problem. It solves the problem you were looking to solve. But then because you've embraced additive, it opens the window to this other opportunity you weren't looking for because of the freedoms that additive brings. And I wonder if anything like that is happening with 3D printed magnets.
Yeah, so that is happening here. I mentioned the blend of material as a challenge earlier, but that could also be an opportunity. So far, most of the printing they've been doing has been with a fixed ratio of that blend of material, but that doesn't have to be the case. With 3D printing, you can actually vary the amount of magnetic material in different parts of the actual part. So that could be a way of conserving that resource, using less of the rare earth elements because you're only putting them exactly where you need to.
So graded magnets are typically used in right now offshore direct drive wind generators. Things like magnetic field, it doesn't have to be everywhere. So based on the modeling, we can see where exactly the strong magnets are needed. That cannot be done by a simple sintered manufacturing, whereas here we think about multi-material processing. That's the future. So instead of just mixing one pellets and do the printing using FDM or a BAAM printer, one can use like more than 2 sources. So you can mix and it'll go through a single nozzle. So you can form like gradient. This way, things where we need strong magnetic field, we can use a dysprosium containing critical material containing magnets so that we generate high magnetic field. And areas where you don't need it, you can reduce the dysprosium composition. So this is the freedom what we have. This cannot be done by a regular manufacturing.
All right, I think I got this. 3D printed magnet. Magnetic materials are rare, difficult to obtain. We get the materials from other parts of the world. Very valuable to conserve material, to use as little material as possible. 3D printing is a means to do that, and the means of 3D printing that looks very promising for 3D printed magnets is extrusion process. Extrusion specifically on the BAAM platform, Big Area Additive Manufacturing. But the bigness isn't the issue here because both small magnets and large ones are made on this platform. Instead, it's valuable for the pellet-fed extrusion process that allows a polymer material to carry this magnetic material. The part is not magnetic when it's 3D printed, then the magnetism is activated later, and a possibility that the Oak Ridge researchers are exploring is a gradient magnet. So don't just use the amount of material you want to use, but obtain exactly the magnetic field you want to obtain by varying the magnetism across different regions of the component.
I think that's it for this episode. Thank you again to Oak Ridge and the manufacturing demonstration facility. You can find more episodes that we're filming here at the MDF at thecoolpartshow.com or our YouTube channel.
Keep watching. Future episodes will be less polarizing. And if you've got a cool part to share, email us coolparts@additivemanufacturing.media.
Thanks again to our sponsor, Carpenter Additive. In addition to supplying metal powders, the company also offers services, software, and hardware to help AM users manage their powder. One example is the Powder Life System, a combination of cloud-based tracking software with hardware designed to make powder handling easier. Two key components are the Powder Life Hopper and the automated docking station. Luke Boyer, manager of Powder Life Applications, and Andrew Holliday, applications engineer, explained how the system works.
So today, when a user of additive manufacturing is receiving powder, they oftentimes receive it in either 5, 10, 15, maybe a 20 kilo bottle. But they're receiving pallets of them, and you're receiving 10, 20, 50, hundreds of these bottles. The user has to look and segregate and store them appropriately so the bottles don't get mixed up. And it requires a lot of lifting and moving and labor.
The components of Powder Life are all based around making powder management systems on the additive manufacturing shop floor easier to use for the operator, cleaner, as well as more traceable. 3 of those basic parts of Powder Life are our Powder Life hoppers, or our storage containers for powder. The second would be automated docking systems that allow material to be pushed in and out of machines with no human contact. And the third would be our Powder Life online software system that allows you to trace this powder as it goes through your shop floor.
The hardware, the software together just helps really streamline that and improve the final user's experience and let them concentrate on going from design to the part itself. Takes the headache of powder management out of the equation for them.